All right, this class, I wanted to do another PowerPoint presentation on the last part of Chapter 15 in the TRO second edition. I'm doing this so that those of you that want to work on the weekend or don't have time during the week to study, I'm going to go through basic solutions and polyprotic acids, and then classifying salt solutions as acidic, basic, or neutral, and the how do we determine acid strength by molecular structure. So we were talking about weak acid solutions and how to calculate either the acid ionization constant or how to calculate equilibrium concentrations based on using the ice table, the initial change in equilibrium of an initial concentration of a weak acid, and knowing its acid ionization constant. So today, let's look at the base. Let's look at something like the common base. Let's look at ammonia. All right. So let's say we have so we're dealing with basic solutions or bases, and we have ammonia. And when we add ammonia to water, when we add ammonia to water, getting ahead of myself. Again, according to the Bronsted-Lowry definition, the hydrogen a hydrogen ion from water is donated to ammonia. We get the ammonium ion plus the hydroxide ion. Okay, if we write the equilibrium expression for this, we get K equals the concentration of the products, the ammonium ion and the hydroxide ion, divided by the concentration of the ammonia. And you may be going, well, what happened to the water? Well, remember, this is a gas. This is a pure liquid, which is, we assume its equilibrium, or we assume its concentration is not changing drastically over the course of the reaction because it's a pure liquid. And then the ammonium ion is aqueous, and the hydroxide ion is aqueous, so they are present in the expression. This particular equilibrium constant, we put a B here, and we call this the base ionization constant. So we've talked a lot about different equilibrium constants. We've talked about K, Kc, Kp. In this chapter we talked about the acid ionization constant, Ka, and now we have Kb, the base ionization constant. Again, in order for it to be called a base ionization constant, you must have the hydroxide ion in the expression. Just like in order for it to be called an acid ionization constant, it must have the hydrogen or hydronium ion in the expression. So let's say we initially start with 0.1 molar ammonia, 0.10 molar ammonia, and we'd like to know what the pH of this solution is, because that's a common thing. We would like to know what the pH, or maybe in this case, because it's a base, we'd like to know what the pOH. So let's say for this question, we would like to know what the pH of the solution is, and we'd like to know what the pOH of the solution is. All right, how do we go about solving it? Well, we solve it like any equilibrium problem. We initially say we have some ammonia, and we have 0 of the ammonium ion and 0 of the hydroxide ion. So the first step we always do, but a lot of times we gloss over it, is we have to calculate the reaction quotient Q, which looks a lot like the equilibrium expression, except we're in non-equilibrium conditions. We're at initial conditions. So I use parentheses to say I'm in non-equilibrium conditions. And again, looks a lot like K. When we plug in the initial values for the ammonium ion, the hydroxide ion, and the ammonia, we would get 0 times 0 over 0.10 molar. Well, that equals 0. So Q is less than K. The reaction quotient is less than the equilibrium constant, or the base ionization constant. So what does that tell us? Well, that tells us the reaction is going to shift in a forward direction to make product until Q, the value of the reaction quotient, equals the equilibrium constant. Now, that's, most of us just zip through this because we know if we don't have any product to begin with, the reaction is going to go in the forward direction. But always keep that in the back of the mind because sometimes you will have mixtures of both reactants and products, and you'll definitely have to calculate Q to determine which way the reaction is going to proceed, either to the left or to the right. So the change here, we know we're going to lose X amount of the ammonia. We are going to gain X amount of the ammonium ion, and we're going to gain X amount of the hydroxide ion. So at equilibrium, that's why we call this an ice table. At equilibrium, this is going to be 0.10 minus X. This is going to be plus X, and this is going to be plus X. We don't really care about the water because we assume that concentration is constant through the course of the reaction. So the next thing, we need to find the equilibrium constant, or the base ionization constant, for ammonia. And generally you'll look this up in a table, and it is 1.76 times 10 to the negative fifth. And then based on our expression up here, the ammonium ion concentration equilibrium is X. The hydroxide ion concentration is X. And the concentration of the ammonia at equilibrium is 0.10 molar minus X. Your initial concentration amount minus the change. All right, my rule of thumb is to look at the power here, look at this number. This would be 1 times 10 to the negative 1. There's a 10 to the fourth difference. So what we do is we're going to assume this X is negligible, that the original concentration of 0.1 is so much larger than the amount we're going to lose in X that we can assume that it is, to two significant figures, still 0.1. That makes it easy for us because now we don't have to use a quadratic to solve for this. So to solve for this problem, we're going to multiply both sides of the equation by 0.10 molar. So I'm going to erase this, and I'll put times 0.10 molar. Remember how math works here is that if you got an equal sign, whatever you do to one side, you got to do the other side. This becomes unity, or 1. And so now what we have is 1.76 times 10 to the negative 6 equals X times X is X squared. All right. We got to solve for X, so we take the square root of both sides. Now, some of you mathematicians say, well, is that legal? Yeah, you do get a positive and negative root when you take the square root of something, but again, we can't have negative concentration, so we focus on the positive root. So take the square root of 1.76 times 10 to the negative 6. So let's see what we get for an answer here. All right, and so we get X equals, I'll flip this around because we generally like to have our variable on the left, 1.3266 times 10 to the negative third, and that is in molarity units. Now we're carrying more significant figures here because we don't want to have any round off error at the end of our calculation, so we'll carry more than what we actually need. So the question was, what is the pH and what is the pOH? Well, let's find out what X represents. So we go back up to our balanced ice table, and we see X doesn't represent the hydrogen ion concentration. It represents the hydroxide ion concentration at equilibrium. So we know that pOH is equal to negative log of the hydrogen, or the hydroxide ion concentration. So we're going to take let's drop down a step here. We're going to take the negative log of 1.3266 times 10 to the negative third molar. All right, when we do that, what do we get? Let's try it out and see what happens. .877. So, POH works like pH. The lower the POH, the more basic the solution is. Just as the lower the pH is, the more acidic the solution is. So this is a fairly basic solution. And it should be because we're dealing with the base ammonia. All right, so how many significant figures should we have? Well, we have 3 here. We have 2 here. So we should only have 2 significant figures. 1, 2. So remember in logarithmic form, the 2 out in front, or the number in the ones place, represents the power, the exponent. It's the numbers after the decimal that represent how many significant figures were in a calculation. So if I was going to polish this up, it would be 2.88. 2 significant figures past the decimal. So my POH for this ammonia, 0.1 molar ammonia in water would be 2.88. Now, the easy way to determine the pH, because it asks for the pH as well, is just to say 14 minus 2.88. So when we do that, we get 11.12. 11.12. Now, without a doubt, everybody knows that's a basic solution. pH of 11.2. It's above 7. All right? So, acids and bases work the same way. You write the balanced chemical equation. You find the equilibrium constant, but for bases we look for Kb. Kb says that in the expression there must be the hydroxide ion. If it's not, you don't really have a Kb. Just as for when we say Ka, we must have the hydronium or hydrogen ion in the expression. You set up an ice table, solve for X. Remember, X is not the answer until you plug it back up into the ice table and see what X represents. So for us, we see that X represents the hydroxide ion concentration. Therefore, when we take the negative log of X, we will get the POH. And to get the pH, we have to subtract that from 14. I hope this helps. And there are other weak bases besides ammonia, and you will need to practice on doing calculations with them. All right. The next concept that I want to talk about is the acid-base properties of ions and salts. Acid-base properties of ions and salts. Well, first of all, what is a salt? A salt is an ionic compound that usually consists of a metal and a non-metal ion, or metal and non-metal, or metal and polyatomic ions, or polyatomic ions and non-metal ions. All right. One way to think about a salt is to look at the salt. So we got a metal with a non-metal. Look at the salt and go, oh yeah, okay, from General College Chemistry 1, I know that what I really have here is, especially if it's in water, what I really have is 2 potassium ions and a sulfate ion. So it's important that you can look at a salt and think about what acid and base combination could I combine to form this salt. So the potassium ion could come from something like potassium hydroxide, a base. Remember that bases tend to be metal hydroxides. If we combine this base with the strong acid, sulfuric acid, you go, how do you know it's sulfuric acid? Well, Acids tend to be nonmetal hydroxides. Here's the nonmetal. This is an oxyacid. If we look at the Lewis structure for this, actually I'm going to do it a little differently. If we look at the Lewis structure for sulfuric acid, it looks something like this. Then we'd have to put in our lone pairs or non-bonding pairs. All right, so here's the Lewis structure for sulfuric acid, and we call these nonmetal hydroxides. So, and what makes it an acid is this hydrogen loses its electron to this conglomeration here because of the electronegativity of oxygen, and it breaks off as a hydrogen ion. So that's what makes sulfuric acid such a strong acid. That first hydrogen that breaks off very easily and reacts with water, or in this case, potassium hydroxide. So when the hydrogen ion, let's just keep with this. When the hydrogen ion comes in contact with the hydroxide ion, the potassium hydroxide, that's going to form water. So the products in this reaction is the potassium reacts with the sulfate, and we get potassium sulfate, although they never actually combine together because this is all aqueous solution, and potassium sulfate is water soluble. So really, in reality, what we have here in solution is two potassium ions and a sulfate ion. And then what we also have is the hydrogen ions combined with the hydroxide ions, and we have to put a 2 in front of this to balance the potassiums out. The other product we get is 2 moles of H2O liquid. All right? So, here's the salt. And yes, if I made these products and then I put this on a stove and heat it up, the water will boil off, and what I'll have left in the bottom of the pan is this salt, potassium sulfate. So, salts can be derived from their acids and bases, in this case the acid and the base. All right, that brings up another point. This is actually from the previous course as well. So in reality, what I have in potassium hydroxide, because it's a strong base, is actually in solution I have these 2 ions. And actually in solution with sulfuric acid, I have this ion and I have this ion. And some of this ion can actually break down even more into another hydrogen ion given off in the sulfate ion. Now again, this reaction, the Ka for this reaction is, we'll call it Ka2, is much, much less than Ka1, which would be this reaction where this hydrogen breaks away from the sulfuric acid. So when I combine these, I get 2 potassium, and we need to balance this. I get 2 potassium ions and a sulfate ion on the product side. And again, these stay separated because potassium sulfate is water soluble. But the hydrogen does combine with the hydroxide ion to form water. All right, so let's look at the reaction. What's happening here is the hydroxide ion is reacting with this hydrogen ion and forming water. It's also reacting with this hydrogen ion and forming water, and that's why we have the sulfate left over, and that makes the salt here, or part of the salt, and then potassium ions here. So from our first course in General College Chemistry, we know that nothing's really changing with the potassium ion and the sulfate ion. They're here present on the reactant side. They're here present on the product side. So if we remove these ions because they do not actually involve a chemical reaction, they're not changing their chemical formula from one side to the other. They're called spectator ions. Spectator. ions. Spectator ions are ions that do not change chemically from the reactant side to the product side. So what do I have left over? Well, I have the two hydroxide ions react with the two hydrogen ions. You go, where are the two hydrogen ions? Here and here, to form two waters. Now, to simplify this, we always write our balanced chemical equation in simplest whole number ratio. We get the hydroxide ion reacts with the hydrogen ion to form water. This is called the net ionic equation. The net ionic equation tells you what the driving force is for the chemical reaction. So, for acid-base reactions, the general net ionic equation is the hydroxide ion from the base, if it's present, reacts with the hydrogen ion of the acid to form water. So, knowing that, we should be able to look at substances like NaCl, calcium carbonate, another salt, potassium sulfide. These are all salts, metal with nonmetals, or polyatomic ions. And you should be able to tell me what acid and base these salts came from. So from sodium chloride, you'd say, well, that's sodium hydroxide reacting with hydrochloric acid, and I get sodium chloride, the salt, plus water. For the calcium carbonate, it'd be calcium hydroxide, reacts with carbonic acid, and I get calcium carbonate plus water. And we'd have to balance that, right? We'd have to put a 2 here. Yeah. Does that work? 5? Yeah. All right. And then this one will be potassium hydroxide with the weak acid, hydrogen sulfide, or hydrosulfuric acid, I should say. Hydrosulfuric. And yeah, I'm getting a little sloppy here. We should definitely be putting aqueous symbols with these. All right, and we would get potassium sulfide plus, again, water. So, why is it important that you can derive the salt from its acid and base? Because what happens when we put sodium chloride in water? When I put sodium chloride in water, does it affect the pH of the water? So let's think about it. You've got a cup here, or a beaker. You've got water. So it's H2O in here. And remember, there is some hydrogen ion, hydroxide ion at 1 times 10 to the negative 7th molar. So we add sodium chloride, and the sodium chloride dissolves. We see the solid dissolve into the liquid, so we get this. And remember, there's a cage that forms around the hydroxide ion. The water's polar, the oxygens being slightly negative or partially negative orient themselves around the sodium ion, and the hydrogens being slightly electropositive orient themselves around the chloride ion. That's what dissolving is. It keeps those two ions from coming back together and forming the solid. Now eventually you can add enough sodium chloride that it precipitates out, and you'll see that pile up at the bottom down here. Alright, so the question is, will the sodium ion react with water and form sodium hydroxide plus the hydrogen ion? And will the chloride ion react with water and form hydrochloric acid plus the hydroxide ion? That's the question. So you look at it and you go, okay, well, look at sodium hydroxide. Is that a strong base or a weak base? Strong base. We know strong bases, like sodium hydroxide, go 100% to sodium ions and hydroxide ions. Because that reaction goes 100%, we know sodium will not react with hydroxide ion and make sodium hydroxide. So this reaction does not happen. If it did happen, the solution would become acidic because you got these free hydrogen ions in the solution. Let's look at the chloride ion and the hydrochloric acid. We know hydrochloric acid is a strong acid. Goes 100%, ionizes 100% to the hydrogen ion and the chloride ion. So, this reaction does not go in reverse. Chloride ion cannot react with hydrogen ion and form hydrochloric acid, so this reaction does not happen. If it did happen, it'd actually make a basic solution. It would strip a hydrogen off water, leaving the hydroxide ion in the solution, which would make it basic. So, here is the rule. The conjugate base of a strong acid will not react with water and form a basic solution. We say it does not undergo hydrolysis or hydrolysis, depending on how you want to speak that. Same thing with the metal ion of the base. It will not react with water and form the strong base. All right, so let's look at another example. Let's look at the calcium carbonate. All right, so calcium carbonate, let's see if I can find an example. I would like to have the Ka for this one in order to be able to do this. Let's see, I don't have the Ka. Well, let's look at this one. This one, I'm going to assume that the calcium has very little effect. Now, calcium carbonate doesn't dissolve very well in water, but when it does dissolve, we get a calcium ion plus the carbonate ion. All right? So, we're going to assume the calcium ion is negligible with pH. It's not going to interact very much with water. And the reason why we know that is if we assume that calcium hydroxide is a strong base. Now, some books do say calcium hydroxide is a strong base and some do not. We're going to take the effect that, yes, it's a fairly strong base. There is no way that calcium 2 positive is going to react with water and form the strong base calcium hydroxide. This does not happen. So calcium has no effect, does not react with water and form calcium hydroxide and hydrogen ions. And again, to balance that out, we'd have to put a 2 there. And we'd have to put a 2 here. Does not happen. But the carbonate ion, here's the question. The carbonate ion, is that the conjugate base of a strong acid or a weak acid? Well, what is the conjugate? What is the acid of carbonate? It's hydrogen carbonate, HCO3 negative. And then as an acid, it could lose a hydrogen ion, and then we'd be left with the carbonate ion. You got to look at this acid. Is that a strong acid or a weak acid? Well, it's a weak acid. It's not one of the 6 strong ones. Hydrochloric, hydrobromic, hydroiodic, sulfuric, perchloric, or nitric. So it's a weak acid. So what that does is that tells this reaction mainly goes in reverse, that this is the dominant species in a water solution. So if this is the dominant species, if I put carbonate ion in water, it is going to accept a hydrogen ion from the water and form the weak acid, the hydrogen carbonate ion. And then what's left over the water? The OH negative ion, which makes the solution basic. So calcium carbonate, when dissolved in water, will make a basic solution. So again, let's recap what we've done here. Um, we take an ionic salt, calcium carbonate. We say that it breaks apart in water. Now, it doesn't break apart very well in water, but it does, a little bit does dissolve. We look at the two ions, calcium ions and carbonate ions, and we have to determine whether these ions will react with the water, undergo hydrolysis or hydrolysis. So we look at the calcium. If the calcium ion reacted with water, we'd form a fairly strong base, calcium hydroxide, and we would generate hydrogen ions. That's what's left over of the water, and the solution would be acidic. But we know strong bases do not stay in their ionic form. They stay as ions. So this reaction does not happen, and so calcium ions have no effect on the pH. On the other hand, if we look at the carbonate ion, we add a hydrogen ion to it. That's what we did here, and that's now an acid. So we look at that acid, the hydrogen carbonate, or sometimes called the bicarbonate ion. That's the older naming system. And we say, is that a strong acid or a weak acid? And we know that that is a weak acid. And we know this, the weaker the acid, the stronger the conjugate base. There's the rule. The weaker the acid, the stronger the conjugate base. So the carbonate ion is the conjugate base of the weak acid hydrogen carbonate. So if we have carbonate ion in water, it will accept a hydrogen ion from the water and form the weak acid hydrogen carbonate ion. And what's left over the water is the hydroxide ion. Well, if we increase the hydroxide ion concentration in water, that's going to make a basic solution. All right? So the salt can actually affect the pH. So what was my other example here? Potassium sulfide. What do you guys think? Potassium sulfide. It's going to make the solution acidic or basic. Well, it dissolves into water as two potassium ions plus a sulfide ion. The potassium ion, if it reacted with water, would form the strong base, potassium hydroxide, and then leave us some hydrogen ion, and it would make the solution acidic. But we know this is a strong base. We know this reaction does not happen. So potassium has no effect on the pH. The sulfide ion, though, let's think about what the acid would look like. It would look like this, HS negative, right? And then we would get the hydrogen ion plus the sulfide ion. So think about this acid. Is this acid a strong acid or a weak acid? Well, it's not one of the 6 strong ones, so this is a weak acid. So yes, the sulfide ion will react with water and form the hydrogen sulfide ion plus the hydroxide ion. So it took a hydrogen ion. Hydrogen ion leaves the water, attaches itself to the sulfur. We get this ion. And we generate the hydroxide ion, so this is a basic solution. Again, basic solution. All right, let's look at one more salt. This is where it gets a little harder. Let's say we have ammonium acetate. Now, some of you might write it this way. Some of you might write it like this. Oops, no positive, just like that. All right. Ammonium acetate. All right, so what happens with ammonium acetate? Well, ammonium acetate's a salt. It's 2 polyatomic ions bonded together. When it dissolves, we get the ammonium ion plus the acetate ion. So we got to evaluate these 2 ions. Do they react with water? Well, So we're looking at the ammonium ion, and it's got a positive charge, and you're thinking, am I going to look at that as an acid, or what's going to happen? Well, this is the conjugate acid of the base ammonia. So here's ammonia. When it gains a hydrogen ion, it becomes the ammonium. It becomes the ammonium ion. So there's the conjugate acid of this base. So what happens here is that we know this is a weak base. This is not a strong base. And so, yes, the ammonium ion will react with water and form the weak base plus the hydronium ion. So the ammonium ion makes an acidic solution. And we see this all the time when people fertilize their lawns or crops with ammonium nitrate. That makes the soil acidic. And then to counteract that at some point, we go back and fertilize or spread on the lawn or crops, the crop field, calcium carbonate or calcium oxide, which is called quicklime, to neutralize the acidity of the soil, to bring it back to a tolerable pH for the plants. So yes, the ammonium ion will react with the water and form the weak base and generate the hydroxide and make an acidic solution. Well, let's look at the acetate ion. The acetate ion, if we look at its origins, the acid that it came from was acetic acid, which can be, again, written like this, or it can be written like this. And acetic acid, strong acid or weak acid? Well, it's a weak acid. So it mainly wants to stay in this form. It does not want to lose a hydrogen ion and become the hydrogen ion plus the acetate ion. Now, it does happen, but it mainly wants to stay in the molecular form. So yes, the acetate ion will react with water, and it will form the weak molecular acid, acetic acid, plus it generates the hydroxide ion. So, the ammonium ion generates an acidic solution. The acetate ion generates a basic solution. And so you may be thinking, well, no problem here. These two cancel each other out, the hydronium ion and the hydroxide ion. So it must be a neutral solution. Well, it doesn't work that way. Maybe this reaction dominates over this one. Maybe this one goes to more completion than this one. So we got to figure out which one goes to more completion. You go, well, how do you do that? Well, we're going to have to look up the Kb for the acetate ion. And we're going to have to look up the Ka for the ammonium ion. And whichever one of these equilibrium constants is larger, that's the reaction that's going to dominate. And that's what's going to determine the overall pH of this solution. So we have to look at a table. So you generally have these types of tables in your textbook. And if you don't have a textbook, you can look at handbooks for chemistry, and they will generally have this information in them. So the Ka for acetic acid, now this is what happens. The Ka for acetic acid is equal to 1.8 times 10 to the negative fifth. And for ammonia, that's the most common form we see, we have to find a Kb for ammonia. So we look in the table, and the Kb for ammonia is 1.76 times 10 to the negative fifth. But for us to explain which one of these reactions is going to dominate, we need the Ka for ammonia, and we need the Kb for the acetic acid. So here's a tool that you'll need to memorize. Ka times Kb equals Kw. And you can prove that by looking at, you could look at the Ka for water. The auto, let's see. You can prove this by looking at two reactions. One, the basic reaction like for acetic acid here, and then the acidic reaction for acetic acid. When you combine those together, you're going to get the hydronium ion concentration times the hydroxide, which will give you Kw. So here you can prove this. You can take the time to prove this, but this is the equation that you need. So for the Ka for the ammonium ion, we would take 1 times 10 to the negative 14th, and we would divide that by the 1.76 times 10 to the negative 5th. All right, and for the Kb for the acetate ion, we would take 1 times 10 to the negative 14th, that's the Kw, and divide that by the Ka, the acid, 1.8 times 10 to the negative 5th. All right, well, we can see now by this, we just happen to choose two ions that have pretty much the same equilibrium constants. I mean, to two significant figures, this is 1.8 times 10 to the negative 5th, too. So, had Ka been much larger than Kb, you would have said this reaction dominates and the reaction would be acidic. Had Kb over here dominated, it was a much larger number than this number, then this reaction would have dominated and you would have said the solution was basic. So for salts that contain two ions that both undergo hydrolysis, we have to look at the equilibrium constants for the two ions reacting with water, and whichever equilibrium constant is larger, that is what dominates the pH or determines the pH of the solution. All right, I hope this helps. I think I'll stop this lecture here and I'll process it and put it on YouTube. The next lecture will be on looking at molecular structure, what molecular structures lend themselves to make acidic solutions or more acidic solutions, and what molecular structures lend to basic solutions. All right.